Our fourth example of a quadratic applications is a biology problem. The metabolic rate of an ectothermic organism increases with increasing temperatures within a certain range. So that's important enough to underline right there, a certain range. Experimental data for the oxygen consumption, C, in microliters per gram per hour of a beetle at certain temperatures can be approximated by this given model. C of x equals 0.45x squared minus 1.65x plus 50.75. Now it also includes for air temperatures 10 less or equal to x less or equal to 25 in degrees Celsius. So that's going to be very important for us when we start talking about domain and range. Let's look at question 1. When the oxygen consumption is 150 microliters per gram per hour, what is the air temperature? So let's go back to the table and figure out what these variables really represent. C is oxygen consumption. And notice how X is used for air temperature. So if we have a given value of oxygen consumption, that means 150 is the output. Make sure you're using 150 for the correct variable. So for part 1, the function is equal to 150. That means 150 is equal to 0.45x squared minus 1.65x plus 50.75. We'll need to put this in standard form, and we can do that by subtracting 150 from each side of the equation. That leaves us 0 equals 0.45x squared minus 1.65x, and when we subtract 150 from 50.75, we're going to have 99.25. We'll use the quadratic formula to solve this quadratic equation. So A is 0.45, B is negative 1.65, and C is our negative 99.25. Substituting into the quadratic formula, negative times b plus or minus the square root of our quantity of b squared minus 4 times the a value multiplied by the c value. And all of those terms are divided by 2 times a. So when we simplify, negative times negative would be positive 1.65 plus or minus these terms under the radical. So we're going to square this quantity of negative 1.65, and that will give us 2.7225. Our three factors, negative 4 times 0.45 times negative 99.25. Since we have two negatives, I know that I'll be adding something. If we multiply those three factors together, we'll have 178.65. In the denominator, 2 times 0.45 gives us 0.9. If we go ahead and simplify this radical by adding these numbers, we're going to have 181.3725, and to be more useful, we really need the decimal equivalent. So using the square root function on your calculator, go ahead and get a decimal equivalent, and I'm going to round mine to just the nearest tenth, so it's about 13.5. So remember, we'll be using this as plus 13.5 and as minus 13.5. So when we write the new equation, x would be equal to 1.65 plus or minus 13.5, all divided by 0.9. Now that looks like something we can work with. One of those equations then would be x equals 1.65 minus 13.5 divided by 0.9. And then the other equation would be x equals 1.65 plus 13.5 divided by 0.9. So we're going to get two decimal values for these equations. When we use subtraction, we'll have negative 13.2 degrees C. When we use the addition, we'll have 16.8 degrees C, because remember, X is our temperature in degrees Celsius. Now at first we might think we actually have two solutions, so let's see if that's true. How do we figure out if we keep these answers or if one of them won't make sense? Celsius can be negative. Going back to our statement here, there was some restriction given. It says that the degrees Celsius had to be in between 10 and 25 degrees. Negative 13.2 does not fall within those values. So we have to eliminate that solution. 16.8 does fall between 10 and 25 degrees C. So that's the only temperature we'll be keeping. So I can fill in that value of 16.8 degrees when the oxygen consumption was 150. For part 2, we're now going to graph our model from this interval of 10 to 25 degrees, and then we'll state the domain and range. So our temperatures for input must fall between 10 and 25 degrees, so nothing negative there. And oxygen consumption could not be negative either. So we'll use just the edges of our graph. Input X was temperature in degrees Celsius, and oxygen consumption is going to be our other axis. And the oxygen consumption was measured in microliters per gram. We'll include scales now. So the temperature can only go as high as 25 degrees, so I'll count by 2s. And to figure out what the largest oxygen consumption is, we need to fill in some more ordered pairs that we generated. So question 1 generated that first ordered pair, and what we haven't found yet is what the actual oxygen consumption is when the temperature is 10 degrees C or 25 degrees C. So we really need to make 2 more calculations in order to complete this graph. Fortunately, we are given the input, so we don't have to worry about using the quadratic formula again. For 10 degrees Celsius would be equal to 0.45 times the quantity 10 squared minus 1.65 times 10 plus 50.75. So remember to use your order of operations. Make sure you square 10 before you multiply by 0.45. So we'll end up with 45 minus 16.5 plus 50.75. So the oxygen consumption at 10 degrees Celsius is going to be 79.25, and that's in microliters per gram. And now we'll evaluate the function with a temperature of 25 degrees Celsius. We'll have 0.45 multiplied by the quantity of 25 squared minus 1.65 times 25 plus 50.75. Again, make sure that you are squaring that quantity of 25 before you multiply by 0.45. So that gives us 0.45 times 625 minus 41.25 plus 50.75. So the oxygen consumption at a temperature of 25 degrees Celsius will be 290.75 microliters per gram. So now we can see that the largest number in the table is 290.75. So the scale that we could use maybe is counting by 20s. That should accommodate all of our values. So I'm going to plot 16.8, 150, and then 10, 79.25. And last I'll plot 25, 290.75. Do you notice in this problem how we don't have an x-intercept or a y-intercept? And that's because we're only graphing the oxygen consumption between the temperatures of 10 and 25 degrees Celsius. So we're only looking at a small portion of the parabola. So we'll have a smooth curve connecting these three ordered pairs. So it's not a straight line, it has just a gentle curving to it, but that's the only piece of the parabola that we're looking at here. And finally, domain and range for question 3. Our domain is the temperature. Again, it's only between 10 and 25 degrees. So we'll use brackets, smallest to largest, remember. The range is the oxygen consumption. So the lowest oxygen consumption was at 79.25, and the highest oxygen consumption here was at 290.75. You can see from this example it is very important to pay attention to the details given in the problem so that you're only graphing what is in the domain and range for that given application.